Welcome everyone. In this video, we're going to be doing a review of the testing notes that I've taken so far during the recon phase of this course. I've stressed a couple times about the importance of taking notes and that I will be adding our findings to my notes. So I wanted to give a chance for everyone to see those notes. And this will also serve as a good review of all the things that we've taken a look at and discovered so far in our recon phase. If you want to see a copy of these notes, they are available in the course GitHub, so you can also get to them through that, and they're in this testing notes folder called testingnotes.md. As I've mentioned before, I always like to include a few test details in my notes about the equipment that we're testing. So you can see here, I've started out with noting the manufacturer, the part number, and then also the serial number. If you're doing this in a professional environment, then keeping track of the specific serial number is going to be important because there might be multiples of the device around at hand and you want to keep track of exactly which one you're performing your testing on. I also like to keep a note of the test equipment that was used. For this course, I think it's sufficient just to list out what equipment was being used, but in a professional environment, you may also need to keep some details about the actual serial number of that equipment because it's possible that there's calibration data or other testing data that's tied to that equipment to certify that it's okay to use for the testing. So we use that multimeter and I've just listed the manufacturer and part number. Same with the logic analyzer, and I've also taken a note of the software that we used. In the initial recon, we started with our visual inspection. We took a look at the router and also the internal PCB. On the outside of the router, the one piece of information that stuck out was the FCC ID, so I copied that ID down, and I've also added a quick picture of it to my notes. After that, we opened up the router case, and we did so by removing those two Phillips screwdrivers and then snapping open the pressure fit container with the spudger tool. I snapped a quick picture of the internals of the router for future reference. I also noted that we saw 3 chips of interest on the PCB for further inspection, and I've denoted those as A, B, and C on this picture. After that, we moved on to the onboard testing. We noted the presence of a test connection that appears to be a UART connection. We based this off the fact that it had 4 pins and they were labeled with VCC, ground, RX, and TX, and this is shown in detail D here. We then verified the operating voltage of the PCB at 9 volts, and we did this by testing the voltage drop across the input jack with the multimeter. We then identified a ground connection on P1, which is detail E here, and we did so by using our multimeter to test the continuity between P1 and the ground on the jack. We then moved on to testing the suspected UART connection with the multimeter. We did so we could verify that the pins matched the silkscreen and they behaved in a way that we would expect UART to. First, we measured the VCC voltage and we found that to be 3.3 volts, which confirmed the operating voltage of the UART at 3.3 volts, which is really important for us to know for our future testing and the equipment that we're going to use to do so. We then verified the ground connection by checking the continuity between the ground pin on the UART, and the continuity test confirmed that that ground is actually in fact a ground. We tested the RX or receive pin by measuring the voltage drop between RX and ground was 0 volts. Just to check that this also wasn't grounded, we did a continuity test between that pin and the ground, and there was no continuity, which confirmed that it was actually at 0 volts. We then measured the voltage on the transmit pin, and during standard operation, we saw it was approximately 3.3 volts, which was to be expected. After confirming that pinout and based on the observations of the pins, we suspected that this actually was a UART connection. We then checked for an output on that transmission pin during boot up by power cycling the router and then measuring the voltage drop over the TX pin during that boot up. I noted a fluctuation on that pin from approximately 1 volt to approximately 3 volts, which suggested a busy and active transmission during boot up. We then soldered our through-hole inline header pins to the suspected UART connection, which is shown up in this picture here. So you may have soldered them yourself, or you may have gone with that twist tie method. Either one is fine. I just kept a note of that. We then attached our logic analyzer to the transmit and ground pins of the UART connection, and we captured that transmission during boot up. Here I've taken a screenshot of a single frame. When we manually inspected the framing of that signal, this confirmed a UART transmission, and we noted the start bit, 8 data bits, 1 stop bit, and no parity bits. We also measured the baud rate as 125,000. So you remember we measured it here, or we could calculate it as 1 over this timing. We then looked up the common baud rates and determined that based on those standard serial baud rates, we suspect that the baud rate for this router is actually 115,200. Based on these findings, we then applied a UART decoder to the channel, and we used the below settings. So again, that's this baud rate, 115,200, data bits 8, parity none, stop bits 1. Just a heads up, you may commonly see this referred to as 8 none 1 for how this is set up. It's just very common to, give the UART connection details or serial connection details as baud rates, data bits, parity, and then stop bits, but they won't actually say what those are. You would just see it written as 115,200, 8, none, 1. Of course, we then decoded that UART signal, and we confirmed those UART parameters were correct because we actually got text back in ASCII characters, and this showed the presence of a bootloader and boot up logs, and we're going to investigate those further. Great finding for us to see these. After that, we moved into our OSINT and online recon. We used that previously located FCC ID to find the FCC equipment authorization filing for the router. So just linked it here. I think it's always good, and I've done this myself, to download all of the PDFs and everything just in case somehow they go offline or something like that. It's good to keep a record of the PDFs, which is something that I have done as well. Of course, we noted in that filing that the ID has changed from this previous TE7 and then the part number. I just got a screenshot of that document. So we then looked in the previous filing, and we found those internal photos of the router. Unfortunately, the schematics, functional description, and block diagram were redacted as confidential. We got these nice pictures of the internals of the router, including these two that showed a very close-up picture of some of the chips in question, and we were able to pull the manufacturer and part number off of those. Unfortunately, the markers on chip C were not readable in the FCC picture, so we returned back to our test router and we took some high-resolution pictures, and we were able to blow up those pictures to ID the chip, and we ID'd it as this Cepheon QH32B104HIP. We then went ahead and looked for the data sheets for each of the chips. So I've got some notes about the first one, the MediaTek. We noted that it was a system on chip, which is commonly referred to as an SoC, and this contained the CPU or the processor. Some of the important details included that this is a purpose-built SoC for N300 routers, and the CPU is this MIPS 24KEC. We also noted the support of these two Linux kernels, and also that it interfaces with the flash memory via SPI. Of course, there was lots more important details in the datasheet, so I've included a link here. I also downloaded this myself. We then checked this Zentel chip and noted that it is the RAM, and we were able to locate the datasheet for it here. Finally, we were able to ID this Cepheon chip, and the full part number for that is listed here. We noted that it is a flash ROM communicating via SPI, and we got the whole datasheet here, which importantly contains that SPI information and the pinout. Next, we did a search for the firmware that we suspected would be loaded onto this ROM, and we were able to find it on the official support page for the router, which I've linked here, and I also saved a download of that. The next thing we moved on to was the initial network recon. We connected our test computer to the network, and we found the router IP address as this 192.168.0.1. We then performed Nmap scans for both TCP and UDP. Got a screenshot of the TCP scan here. We found there was the 3 ports open, the port 22, which is SSH, running the Dropbear and the version. That port 80 was HTTP, and we noted that it is hosting the router's configuration web portal. And then we also found port 1900, which has the UPnP and a little bit of versioning for it. One notable detail that we found was that this confirmed our suspicion that the router is running this Linux kernel 2.6.36. We also did a UDP scan, and we revealed 2 ports on it, this port 67, which is the DHCPS, and the UDP port of this UPnP. We then wrapped up by doing some scouting on previously disclosed CVEs, and you may recall in those previously disclosed CVEs, we noted that there was a common theme of a lack of proper user input validation on forms and inputs in the web portal that led to either buffer overflow or command injection of an underlying function or service being called. I then put a link to this list on OpenCVE of all those CVEs and the 2 blogs that we found about the interesting CVEs. That wraps up all the notes that I've taken. If you took different things or more details, then good on you. I would say the more details, the better for these notes. We're definitely going to be relying on these notes and coming back to them frequently throughout the rest of the course. That wraps up this video and also the recon portion of the course. I'll see you over in the next one.